Okay. Okay, so it's a great pleasure for me to introduce Professor Evgeniy Khain from the Department of Physics at Oakland University. Professor Khain is at Oakland since 2007, where he started as assistant professor, now he's assistant professor. He was postdoc earlier on at the University of Michigan, Ann Arbor. So Professor Khain is a great expert in statistical physics and nonlinear physics, in particular in the study of collective behaviors of cells, including mechanical effects and growth. Which is something actually which is of interest at the animal level, organismal level for me, but also is interested in instability problems in granular flows, in rare events, front propagation, pattern formation, many applications of nonlinear physics and statistical physics. And today is going to talk about spatial period of an epidemic. And so thank you very much for the opportunity to have you here.
Thank you very much. Thank you very much. It's a pleasure to be here. So I'll discuss some of my research on epidemic propagation, spatial propagation of epidemic, and there will be two projects I will be discussing. The new interesting thing in the first project will be that the epidemic is put on networks, so people communicate with each other via a network of contacts. So I'm from Oakland University. Here is a map of our region. Yes, you see, Lake Erie, Lake Huron over here, Detroit. I live in Ann Arbor over there, and here is Oakland University, a bit north to Detroit. So I live in Ann Arbor, and I'm commuting to Oakland University and back, which is quite a commute. And I'm indeed, as Alexander mentioned, I'm indeed interested in front propagation phenomena in many different contexts. One of them is cell migration. So the idea here is that you can put cells in the left part of a channel and see how those cells divide and propagate and migrate to the right part of a channel. And this can be described by a front. So you have a front of density of cells moving from left to right. This is an experimental image where cells migrate when maintaining contacts with each other, like just a medium. Cells also can migrate individually, and I worked on both types of those problems. So the question here is how fast the interface propagates and what does determine the speed of that interface. I'm also interested in this phenomenon from propagation in a more general context, studying fluctuations. So on top of doing particle simulations and studying how the speed of front propagation or what's called front wandering depends on the number of particles in the system. And I also teach about front propagation. I'm teaching a graduate class, and one of the topics is front propagation and Fisher-Kolmogorov equation and Ginzburg-Landau equation. These are two nonlinear equations from nonlinear dynamics, which describe spatial front propagation into an unstable state and into a stable state, and I will mention it today. So in the context of epidemic, I'm imagining the following situation. Suppose you have a spatial coordinate, and in this spatial coordinate you have villages. So every big dot here is a village, and there can be an outbreak in the village. So the village can be healthy, but then the first village can get an outbreak. And since people are moving from village to village, yes, I live in Ann Arbor and work at Oakland, then this outbreak can propagate, and then the next village can become infected, and the next village can become infected. So you have a pulse of infection propagating, And then the village, behind the front can become recovered. Yes, and then the next village behind the front becomes recovered. So you see that you have a pulse of infection propagating throughout the system, and the question is how fast this happens. And now this phenomenon of front propagation generally is divided in two big classes. In one, the front propagates into linearly unstable state. In our context of epidemics, it means that even if you have a small fraction of infected in a village, there will be an outbreak. And the second class is when the state of no infection is linearly stable. It means that if you put a small number of infected, the outbreak decays, and so there will be no outbreak, the infection decays, and you need a fraction of infected to be above a certain threshold for the infected, for the pulse to propagate. And I will discuss both of those cases. So those two projects were published in PhysRev 2 years ago. And in the first case, what I'm interested in is in considering networks of contacts between people. So a network of contacts is just, you see here you have a number of nodes. Every vertex, every node here is a person, and you have contacts between those nodes. So for example, this person number 7 has 1, 2, 3 contacts. Yes, but this person number 5 has 1, 2 contacts. And the number of contacts is called degree. So there are nodes with different degrees, and the network is described by node degree distribution, which means what's the fraction of nodes that has degree, I don't know, 5, or how many people have degree 7, yes? And so what I'm imagining is that in every village, I have this network. Therefore, locally, the infection spreads not in the mean field equations as people usually do, but on a network. Yes, so this person can become infected, and that it can infect its neighbors, and so on. And so I'm describing the network, and then okay, so maybe some motivation for dealing with the network and not the usual well-mixed population. So usually when we write down SIR model, it's the standard model for epidemiology. It's a model for the number or the fraction of susceptible S, infected I, and recovered R. And these are the equations. So, for example, in those equations, you see that dIdt, the fraction of infected, will increase if an infected person meets a susceptible person. So this first term is proportional to I times S. And then those infected people recover after some time. So here is the recovery term. So if this first term is larger than the second term, dIdt is positive and the infection grows. And then dsdt has the same term as dIdt, but with a minus sign, because if you have, if a susceptible person meets an infected person, then you have one more infected and one less susceptible. And in this type of equations, what we assume is that it's a well-mixed system, so it assumes that every person has the same number of contacts, and therefore the same number of probability of being infected, which is of course not true, because people with many connections in this network language, high degree nodes, they have many more contacts, and therefore their chance of being infected is much larger. So this part is ignored. The network structure is usually ignored. So locally, it doesn't matter if you have a network structure like this, or you have a mean field model. You can run this SIR model. Basically, you say that if this node is infected and this node is susceptible, then the susceptible node can become infected with a certain probability. And then the infected node recovers with a certain rate. Yes, so the same idea can be done on networks, and you get the same qualitative result. So here S becomes I with a certain rate, and in I, the infected person recovers. Here I assume that it's not with a certain rate, but after a certain disease duration. And then you see the standard figure for the S, I, and R as a function of time. So I first was 0, and then there is an outbreak, and then the outbreak decays, and I becomes 0 again. Yes, and S was 1 because everyone was healthy, and after the outbreak, S, the number of healthy people who got the disease, who didn't get the disease, is really tiny. Yes. So that's the typical result for a single network, but now I'm considering a spatial system, which is much more interesting. And the idea is that people move around, and a person from here can get over here. So, for example, an infected person at site n-1 can get to site n and infect people there. And there is an interaction parameter d with this underline d bar, which tells us how strong this effect is, how often people move around and potentially infect other people at different sites. Therefore, you can see that once the first village becomes infected, once there are enough infected people there, this interaction leads to the second village being infected and the third village and so on. And then we have a path of infection propagating throughout the system. So this here I am showing the results of Monte-Carlo simulations. Yes, so what you do in Monte-Carlo simulations, you prepare a network, and on this network, you prepare a network on every spatial site.
So,
and then
can I ask you a question? Like, is the in the current example, is X discrete or continuous?
So, so in the theory, I will be, deriving X will be continuous, but in particle simulations, N is discrete. Yes.
Okay, good.
So I always like this interplay between discrete and continuous systems. Yes, when you do simulations, Monte Carlo like simulations, yes, it's always discrete, and then you derive a continuum equations and compare. So what you do here, you prepare a network for every village, yes, for every spatial site, and then you infect some people in the first site, and then the infection starts propagating, and you get a single run. Yes, and then you do many such runs and average over the results. So here I'm showing the results of 5 runs, 5 single simulations, just to show that it is stochastic, probabilistic. So the results are similar with to each other, but not exactly the same. So, for example, in this figure, you see I as a function of x and t. So the spatial coordinate is x, or the n, the number of villages. And you see I, which is this pulse, which goes up and goes down at 2 different times. This is the early time. So initially, you see this village number 20 has a lot of infected, yes? And this village number 10, everyone has already recovered, so there are no infected. And this village number 40, the pulse of infection didn't get to that village yet. So you have a pulse of infected, a spatial pulse at early time. And later on, this pulse propagates to the right, and this is the pulse for later time. Yes. So you have a certain number of villages, yes, that are infected. Behind the pulse, those villages are already healthy because the infection passed. Before the front, the infection pulse didn't get there yet. So you have a pulse which propagates to the right. And this is exactly the front propagation that I'm interested in.
So here, what's the x-axis? Is the
X-axis is the spatial coordinate, the number of villages. Yes. So you have a propagation of that pulse. The pulse at early time is at village number, peaked around village number 20. A pulse at later time peaked around village number 100. So the pulse, as a function of time, propagates to the right. And the same idea you can see when you plot the fraction of recovered. Yes, the fraction of recovered at early time, the fraction of recovered, for example, here the fraction of recovered is 0 at early time because, yes, for this front, because the infection pulse didn't get there. So there is no one recovered because no one sick yet, yes? But at later time, the fraction of recovered is large, say 90%, because 90% of population got sick and got recovered. Yes? So you have the same front propagation in all those variables, and the pulse moves to the right, and we need to understand how fast it moves. And there are different ways of measuring how fast it moves. For example, you can choose the rightmost particle here, the rightmost particle here, do the position of this particle over the position minus the position of this particle, divided by the time difference, and you see how how fast this front moves. And this is the front speed for a single run. Yes, just a single simulation, spatial simulation with network on every side, yes, and a pulse propagating throughout the system. And then you can measure the speed distribution because you have a certain speed for a single run, and then you do many runs, say 500 runs here, and you can measure a speed distribution. We will be mainly interested in the average speed, but I just want to show that it's indeed a speed distribution. It is relatively narrow, and it becomes more and more narrow if you increase the number of nodes in every network. Yes, so when the network becomes larger and larger, yes, the distribution becomes narrow, and it should collapse to some delta function. Yes, and we are interested in this mean speed. And then
sorry if I stop you again. Just to make sure I'm understanding. Here we have one spatial dimension, correct?
Yes.
Yes, and then you have a diffusive term in each of the three equations of the SIR model. Is that correct?
Well, it's not exactly diffusive term. I will derive the effective diffusion. What you have here is in some sense an effective diffusion, because what I'm saying is that this person can get over here and infect this person and get back. This indeed will lead to an effective diffusion, but this should be computed, yes, and I will theoretically derive it, yes. So in some sense, yes, the idea is this exactly. And one can measure this front of pulse propagation, which is the vertical axis here, as this interaction parameter d, which tells us how often, yes, we have those interactions between neighboring villages. And you can measure the front speed, so those dots, those red, I don't know what it is, squares, are simulations. And this is the dashed line is the theoretical prediction that I'm going to derive now. Any questions before I get to the theory? Okay, nice. So now I need to say a few kind of general words about front propagation into into an unstable point, an unstable state. The famous equation that describes kind of the basic equation that describes the front propagation into unstable state is called Fisher-Kolmogorov equation, and it is the reaction diffusion equation here in the left corner. So the first term is the diffusion term, the second term is the proliferation term or reaction term, and you can see what's the structure of this term. You can see that if u is 0, this term is 0. So if you have, say, no particles, they don't divide. But if u is slightly larger than 0, then this term is positive. Since this term is positive, du dt is positive and u increases. So u equals 0 is an unstable state. And the question is how we describe front propagation into that unstable state, and what is the speed of this front propagation into the system. So basically in the system. So basically you can imagine having a front which is shown in this figure. U is this variable, the x is the spatial coordinate. And you see that, you know, on the left hand side u equals 1, on the right hand side u equals 0, and then the front, you know, connects u equal 1 state and u equal 0 state, and it moves to the right with a certain speed. The question is, how do we determine that speed? Now, there are two, you know, ways of determining this. One way is doing linearization. I mean, the standard way is doing linearization near the 0 state, and then making sure that the behavior is exponential rather than oscillatory. Here, I'd like to convey the same point using some physical analogy. So when you substitute into this equation the ansatz of a propagating front, so u depends not on x, not on t, but on x minus ct, you get this equation. And this equation looks similar to the mechanical analogy, to the equation for a particle moving under a certain force with friction. And this force is a function of coordinate, and in the same way, this kind of force, yes, effective force, is a function of u, and we can compute the potential corresponding to that force. And the potential looks like this. So the potential has a minima at u equals 0 and a maxima at u equals 1, because the force equals 0 when u is 0 and u is 1. And the front profile connects the point u equals 1 to the point u equals 0. So we need our trajectory to start at u equals 1 and get to u equals 0. And the main question is, how does this trajectory look like, the trajectory in this potential? And when, you know, a particle goes downhill with a friction, there can be two qualitatively different situations. If the friction is small, the particle goes downhill and overshoots and then oscillates, and then oscillations decay and you get to 0. But this is forbidden, because if you have oscillations, it means that you get to the region where u is negative. And u in our case is the number of particles, or number of cells, cannot be negative. It means that the friction coefficient, the effective friction coefficient, should be large enough so that we don't oscillate. It means that, you know, when you see the friction coefficient here corresponds to the front speed here. Yes, the analogy for the friction coefficient is the front speed. This immediately means that you should have a minimal front speed in that system. And this minimal front speed, when you do the analysis and check that there are no oscillations in this equation, is just 2 square root of alpha d, where alpha is a proliferation coefficient and d is the diffusion coefficient. So our system it's completely different, yes, but it has the same nature. We have a pulse of infection propagating into the unstable state. Therefore, I'd like to understand what is the effective proliferation and what is the effective diffusion coefficients in our system. So the proliferation would mean that, you know, you put some infected in this village, and the number of infected grows. So you have an outbreak. And this growth rate is exactly our proliferation coefficient. The effective diffusion, you need to, you know, we need to work on this a bit and to see how this effective diffusion is related to this interaction parameter. And once we theoretically get the effective proliferation and the effective diffusion, you do 2 square root of this times this, and you get the front speed.
The basic reproduction number must appear at certain point.
Well, so you see, the basic reproduction number, it is something that you would see when you do a mean field description. But here you have a network, so of course you have the parameters which are the transmission rate and the recovery rate, but also you have some parameters related to the network structure, like you know, what's the average number of first neighbors, average number of second neighbors. So it's more complicated, but the idea is there. Yes, it's the same idea. Yes. So now I briefly show some math, which so first of all, I'd like to understand what is this proliferation rate, and for this we need to work with a single village, with a single network. Yes, it's a property of a single network. You put there some infected, the fraction of infected initially spreads exponentially. This exponent is our proliferation rate. Since we work with the network has different groups of nodes, because there are nodes which have 1 degree, 1 contact, and there are nodes which have 2 contacts, and nodes which have 3 contacts. And people use degree-based approximation for the number of susceptible of degree k. Yes, number of healthy people of degree k, number of infected people of degree k, and number of recovered people of degree k. And you do this for every degree k, yes, for every number of contacts k. So you have that system of equations for every k. Previously you have the system of equations just for the general number of S, I, and R. And now you have a system of equation for Sk, Xk, and Rk. And in this system of equation, one important quantity is the probability that if you take a susceptible healthy node, the probability that its neighbor is infected. So everything is written in terms of this probability, and this probability can be computed like some average of the number of infected of different degrees. Yes, so if the node is susceptible, it has many neighbors, say it has many neighbors, and every neighbor can have different degrees, so it can have different probability of being infected, and you need to do a certain average. This quantity is V. Once this V is written down, you can write down the SIR equations like before, but for Sk, Xk, and Rk. So these equations are relatively intuitive, and it's not difficult to explain what's going on. So Sk is the number of susceptible people of degree k. And this number decreases if a susceptible person of degree k has an infected neighbor. So the chance that the number of susceptible people is Sk, the chance that the neighbor is infected is V. So therefore, it's proportional to V times Sk. Now, this susceptible person has k neighbors. Therefore, we need to multiply by k. And gamma is the probability of transmission rate. Yeah, so this is the term, and it comes with minus because the number of people, number of susceptible people decreases if one gets infected. Exactly the same term with plus you have in the equation for xk, which is the number of infected people of degree k. Now, interestingly, this is a delay differential equation. And this is because here I assumed a constant disease duration. Let's say every person is sick for 2 weeks. This is a more accurate representation of a rate, because a rate would assume an exponential distribution of disease durations. And we know that disease duration is peaked around some value, so I just decided to take a constant disease duration. Now, if you take a constant disease duration, then what happens is that at this moment now, people who got recovered are people who got sick time t capital before. Yes, therefore it is exactly the same term, but time t capital before. Yes, these are the people who got infected now. Yes, the people who got infected time t capital before now get recovered, and therefore it's the same term with t minus t capital, and the same for the recovered. So this is the system of equations, and the nice thing about it is that I'm not interested in solving this for in general. I'm interested just in the initial growth rate. So I can linearize that system around xk, which is very small, yes, and v, which is very small, and see how initially this growth occurs with which exponent. And this is what I'm doing here. Epsilon is some small parameter, and you can see that s decreases as 1 minus average degree times epsilon, and I plus r increase as an average degree times epsilon. So initially the infection increases proportional to epsilon. And for this epsilon, you can write down a linearized equation. And this is a linearized equation. Still, it is a delay differential equation, but assuming the exponential term, because it's linear, so it should grow exponentially, you get this transcendental equation for r, which is the growth rate. And this growth rate also can be explained intuitively a bit. So let's just focus on this prefactor. Gamma is the transmission rate. So clearly, the larger the transmission rate, yes, the larger the growth rate of epidemic. This function g1 prime at 1, g0 and g1 are some distributions related to no degree distributions. And in particular, this number has a meaning of average number of second neighbors for the node divided by the average number of first neighbors. So if you have a node, it has, say, certain number of first neighbors and then certain number of second neighbors, which means that it tells us how fast the network, expands. And this, so how many people you can infect. And this certainly plays a role in the infection parameter. In addition, you have a correction because T capital is the time for recovery. So if T capital, the recovery time, is really large, then people almost do not recover, and you have just this term. But if T capital is not that large, yes, then people recover, and you need to subtract something from this growth rate. So this is the growth rate. And the second thing I need to compute is this effective diffusion coefficient. So you can do the following trick. You can write down what's called an effective master equation. So an equation for the following quantity, for the quantity I of n and m. I is the fraction of infected, n is the spatial coordinate, and m is the time step. So this I of n and m tells me what's the fraction of infected on this side at time step m. And then I'm interested in how this fraction of infected depends on time. Therefore, I want to compute what's the fraction of infected at the same site at time m plus 1 and subtract the fraction of infected at time n, and then I get the change in time. And this change in time is due to two things. First of all, we have a local growth, yes, with the coefficient r, like we computed just before. If you have number of infected I, yes, this local growth is Ri. But then we have these effective jumps. So a particle, an infected person from site n minus 1 can get to site n and meet with a susceptible person at site n. And this happens with the probability I of n minus 1 times S of n times this interaction parameter. Or a particle from site, a person from site n plus 1 can get to site n and also can meet a susceptible person. This happens with this chance, again with this probability, which is the interaction parameter. Since we are interested in front propagation to the zero state, where where I is very close to 0, yes, a state where I is close to 0, when I is close to 0, S is close to 1, yes. So we have propagation to the healthy state where S is almost 1, so I can assume that S is 1 there. And if F is 1, you see that you have I of n minus 1 minus plus I of n plus 1. You can subtract 2in and add 2in, and this is the second derivative term. And that's how you have the second derivative term with the coefficient d, yes, in this equation. And then you have an addition to the local growth, yes. So 2 times d bar is added to the local growth. So this if an infected person comes to our site and infects someone, yes, then local infection grows. So you have this interaction parameter affecting the growth rate too. So we computed, and then the left-hand side is the time derivative, yes. So this is the effective master equation, and then the diffusion equation obtained from here, the reaction diffusion equation. And then we got D, we got the local growth, and then we say that this time this is the speed of front propagation. Actually, it's more complicated than this, because it turns out that the fourth derivative correction is important. So I computed the fourth derivative term, and then there is a correction to the front speed, but overall we got it correctly. So this is the first project where we considered fronts in pulses of infection propagated in a spatial system, and the system consists of many networks which are weakly coupled by diffusion. And we got fronts which are similar to those of Fisher-Kolmogorov equation. So we determined the local growth rate, assuming the constant disease duration. and we computed the effective diffusion coefficient, and then we got the front speed. And we got a nice agreement with simulations. Now I'd like just to very briefly, I think that this is the project I discussed in this that meeting. So I thought maybe I don't need to do too much of this. So I'll just briefly show what's going on, maybe to remind you. So the idea is that the state can be linearly unstable or linearly stable. So if you solve an equation d and dt equals f of n, if f here, yes, if f is 0, yes, the points where f is 0, those are steady states. But if d of dn is positive, this is unstable. But you can have a situation where d of dn is negative, and then this state is stable. This is called an Allee effect. So it means that if n, in this case, is larger than 0, d of dn is negative. And then, so if n increases, yes, f is negative, dn dt is negative, and then goes back to 0. So this state is stable. And this happens in nature and biology in the context of population dynamics, because it is known that some species, they have a certain group dynamics, and their reproduction rate depends on the size of a group. So if the group size is small, the reproduction rate can be lower than the death rate, and then the reproduction stops. So it means that the state goes to extinction. It means that the state of 0 number of those animals is stable. However, if the group size is large enough, the reproduction rate becomes larger than the death rate, and above a certain group size, you have reproduction. The same thing can happen in our situation. So I'm writing down, the simplest SIR equation for di dt. Yes, that's the first term, which is the transmission of infection. S is the fraction of susceptible, I is the fraction of infected, and you have a certain coefficient, which is the transmission rate. And then here you have the recovery rate. So initially S is very close to 1. Therefore, we basically need to compare this R with this alpha. So usually if R is larger than alpha, you have infection. If R is smaller than alpha, you don't have infection. Yes, that's the reproduction number you mentioned. But what can happen is that this R might be a function of the fraction of infected. This can happen due to some measures, public health measures, which are taken when I is small. Because when I is small, we can very efficiently do a few things, say quarantine people, trace the chains of infections. All of those measures decrease the transmission rate. When the fraction of infected becomes large, all this is not feasible, and the transmission rate becomes higher. Therefore, if you assume that the transmission rate as a function of fraction of infected increases, you can see that, if this, I'm doing R over alpha. So when R over alpha is above 1, so we are in this region, then there is an outbreak. But if we are in this region, R is smaller than alpha, and there is no outbreak. So if I must be larger than I critical to have an outbreak. Yes, so this is exactly the idea of Allee effect, or propagation into a stable state. Yes, so state of 0 infection is stable. This is an interesting thing. And what I was doing here, I was computing the front propagation into that state, which is linearly stable. And here I didn't assume any networks, so I was just solving two coupled PDE SIR equations with the diffusion terms like you suggested before. And I was looking for the pulse of infection. And this on the right-hand side, you can see a pulse of infection. So you can see the vertical coordinate is the fraction of infected. The horizontal coordinate is the spatial coordinate. And this is the original profile, the red one, red dashed line is the original profile. So you infect, some villages, yes, and then other villages are healthy. And then with time, if this pulse is developed and it propagates to the right. So this is this is the initial time, later time, later time, later time. So you have a pulse of infection propagating throughout the system. And here there are some interesting observations which I probably will not go into. The thing which is not trivial here is it turns out that you can have two solutions, two propagating fronts, and for the same parameter. So you for the same set of parameters. So you choose a certain parameter and you see that you have two front speeds, this and this. And when you solve equations numerically, you only observe this front speed. So this solution is unstable and this solution is stable. So it turns out that there are two solutions for some reason. And, we, of course, when you solve the system numerically, we see only the stable solution. But the fact that you have two solutions leads to an interesting situation, because when you change the parameter, you have a certain bifurcation diagram. And in this bifurcation diagram, we see that above a certain parameter, so for some parameter regimes, you don't have any solutions for front propagation. And then you ask, okay, so what's going on? If you infect some people on the left part of your system, what happens if the pulse of, and there is an outbreak, yes? So I is above I critical, so there is an outbreak. What can happen? So when you do numerical, when you solve those equations numerically, you see a very interesting phenomena. You see that, so this is your initial fraction of infected profile. And you see that there is a pulse of infection, a big, strong pulse. So there is an outbreak. And this pulse of infection starts propagating. And while propagating, it becomes lower and lower and finally disappears. So it's a new regime of parameters, something that I haven't expected and I never heard of. A situation where you have pulse of propagation, yes, front propagation that slows down and stops and decays, which means that some villages over here never get the infection. Yes, so it's kind of a transient phenomena where so in some sense it's an interesting result, because it means that if you apply some health measures locally, it might not help you, but maybe it helps some people far away, because this pulse of infection will not propagate. Yeah, so this is just kind of a brief idea. And what I'm doing now, working on now in particular, is I'm trying to understand this phenomena in more detail, both on networks and not on networks. So I'm continuing working on this phenomena where the fractional infected depends on the transmission rate depends on the fractional infected. Well, so thank you very much for your attention.
Okay, so thanks a lot for the great presentation. So I'm gonna start with one question, maybe a couple of slides before, when you talked about the two different regimes, right? The previous slide, probably just yeah, this one. So I have a question here. So how many stable equilibria are there when R is given by that formula?
So when R is given by that formula, is what you have is this situation. Yes. So there is a stable equilibrium which is I equals 0. Yes, because the IDT becomes
Right. Yeah.
negative, and I equals 0 is the stable equilibrium. Now, what happens above this? It's hard to call it. I mean, usually you would call this another stable equilibrium. Just like when you do it over here, here is one stable equilibrium, here is
Right.
another stable equilibrium. Now, what happens over there, you have a stable equilibrium in a sense at the very end, which means that, you know, you have an infection, you have locally, you have an outbreak, 90% of people got sick, the infection passed, and this is your stable equilibrium, which corresponds to I equals 0, but it's not the same I equals 0 as before. You can have I equals 0 and S equal 1, so nobody is infected, just the infection didn't develop. Or a state which is I equals 0 and S final, which is very low. So in that sense, you have two stable equilibria. You just don't see it on this figure. Yes. So either no infection and everyone is healthy, or no infection after the front moved, and and many people got the disease, and but because now they are immune, yes, in this SIR model, this is a stable equilibrium.
Awesome. So there was another thing, like in when you did your approximation with S equal to 1, a few slides before this, in the
Yes.
previous problem, I think. So, well, as a matter of fact, you can always write the, yeah, exactly. So in the susceptible equation, in practice, you can solve the susceptible as a function of the infected. So, and you end up having in practice an exact equation there, not an approximation. So maybe that you can just write it an exact formulation also in this case. I know that you start from the master equation, so it's discrete version, so it's slightly different, right? But maybe you can write your equation without the approximation of S equal to 1. So the dynamic, the approximation is valid not only initially.
You see, the situation is the following. In this theory, I don't need it because the front profile is computed from the linear system. When
Right.
you linearize, you assume that I is close to 0. Yes, you are linearized around 0. When I is linearized around 0, S is linearized around 1, and therefore it's basically I equals epsilon, and S is 1 minus epsilon, which and then the front speed is obtained from the linear system. However, of course, when you propagate into when your state is nonlinear, then yes, and then it's a different story. Yes, so here I'm not linearizing, and I'm also not solving for this. So I can solve those equations only. So mathematically, okay, so you can solve them numerically. Mathematically, what I do, I'm substituting these ansatz. And once substituting these ansatz, I'm getting two coupled second order ODEs.
Right.
And then this is a 4D dynamical system. And then I'm trying to do some shooting procedure in MATLAB to find the front speed. So here, I don't know if it is possible to solve for S as a function of I, because the parameter is not is a function of I. Yes, so I don't know how this is done in that system. You know, if you can do it here, I'm not sure. it's a,
Well, it
you know,
probably depends on the shape of the functional expression of ROI.
yeah, yeah.
If ROI times I is kind of invertible, then somehow you can technically have even a weird formulation, but you might have end up with a single equation, maybe non-local one. I don't know.
So you see,
Yeah.
one interesting, you know, question, very interesting to me, is that when you solve this, yes, sometimes the front profile exists, so sometimes C exists and sometimes is not, and if you know, if one can do some theory around this point, this would be very interesting. But
That looks like a saddle node bifurcation.
Yes, but even I even cannot find, you know, cannot find the point. Yes, I find it numerically. I cannot. I find it numerically. I find it, you know, semi-analytically from this analysis of on the phase plane, but it's not. You know, I cannot write an equation, yes, or some complicated differential equation just for this problem point and solve. Yes, so and so of course it would be interesting to do this and then do some expansion around it. Yes, but I don't know.
I have also another question about this, right? You have basically two speeds of propagations there. One, do you know where if they go both pools go in the same direction?
Yes, it goes the same direction. It's just,
right,
you know,
because these are
this
poles,
speed is larger, this speed is smaller, so the larger speed is what is realized in real life. Yes, and the smaller speed is not. So I have two trajectories, two front trajectories. Yes, so and I've checked that the correct front trajectory, yes, the blue one, if you choose this speed and the corresponding front profile, I've checked that it exactly fits with the solution of numerical solution.
So there are situations in like dynamical system which admit like soliton, multi-soliton solutions, right? In which you can write many linear combination of pulses and something like that, right? Linear combination of waves or something like that, right? And then you get them still to be equations, solutions. But here I would be surprised if that's the case because the nonlinearity is a little bit weird.
Yeah, it's non-linear. We just have two different front profiles. So we have two different trajectories in the phase plane. Yes, you need to solve equations for I prime, S, and S prime. Yes, two, and so you can put those trajectories on the phase plane, and you have this blue trajectory which is stable, which is what's realized, and then the black trajectory which is unstable. So for every parameters you have those the two trajectories, apart from parameters over there where you have none. Yes, no trajectories, because there is no front profile at all.
Okay, great.
Yeah, interesting.
So thank you very much for the great presentation. Let's thank Professor Khain again for the great talk. Thank you very much for the opportunity to hear about your research.
Thank you for inviting me. Let's be in touch. Okay.